forget to do so. I'm going to welcome everybody to this month's CARE Acoustics Seminar, and glad to have somebody from my home state of Oklahoma joining us today. I do want to remind everybody that next month, we're already into November. It's hard for me to fathom. We're already through November this year, but we'll have another seminar. Our last seminar of the fall semester will be next month. It'll be on December 8th, and it's going to be Susan Parks is going to be joining us with a talk about acoustic communication in North Atlantic right whale mother calf pairs. That'll be interesting and quite a pivot from what we learned about today. Today we have Dr. Brian Elbing with us, and he's an associate professor of mechanical and aerospace engineering at Oklahoma State University, our land grant sister school in Oklahoma. He has his master's and PhD in mechanical engineering from the University of Michigan, as well as a BS from Western Michigan University. And his research is focusing mostly on identifying fluid mechanisms within complex high Reynolds number flows. And his talk title today is The Search for the Silent Sounds of Tornadoes. And I'm really excited to hear Brian talk about this. Again, as a resident at home, what we call an Okie, being from Oklahoma, we're always kind of watching over our shoulder for tornadoes. So I'm curious to hear about Brian's research. Brian, really appreciate you joining us today to hear your exciting science.
So. Thanks for the intro. Yeah, I'm excited to share with you the challenges and successes that we've had with this project. It's a interesting one. So basically, my goal for this talk is kind of give a big sweeping overview, both on the research side as well as some of how I got involved with it, because I kind of assume with these talks there's always going to be a decent chunk of students that attend as well, and I like to give a little bit of background in how pieces at different times can have a significant impact on your life. And this project in particular is a good example of that. So we'll just dive right into the material, starting with motivation and background. So when I think about tornadoes as a fluid dynamicist, they're really just small, turbulent, coherent structures that rarely occur. They're extremely rare. To give you a sense that they're small, I'm showing this one large storm system, and then I kind of circle these two tornadoes that are happening inside of this one larger storm system. So you get a sense that, yes, they're big to us, but no, in the grand scheme of things, and compared to the atmospheric boundary layer or storm systems, they're small features. And so essentially, that makes it hard for us to identify them and study them. And we really wouldn't care about them at all, except for they're catastrophic to us. These are some examples of what they can do to houses and neighborhoods. And obviously living in Tornado Alley, where this is intimately aware of such possibilities. In 2019, actually, we were on track for a historic year. It slowed up a bit, and we ended up in just the 75th percentile. But actually, Professor Howard, before this talk, he was saying that he was in Oklahoma in 2019, and they kept having to stop their work because it was tornado warning after tornado warning, which is certainly true. It was a hectic year. But it's important to realize that tornadoes are not just limited to Tornado Alley or even Dixie Alley. Even if you look up in New Hampshire, you don't get many, but there are a few dots. This is like a 10-year window, and even New Hampshire, you've gotten some tornadoes. Tornado Alley, which is more famous, where we get the largest, most dangerous tornadoes in terms of size and strength. But actually, a lot of my work, the motivation behind it is really focused on Dixie Alley. They get smaller tornadoes, but they get a lot less warning. And as a result, the majority of deaths in the United States today are really associated with Dixie Alley. Georgia, Mississippi, Alabama, they get these tornadoes that kind of prop up at night. There's hilly terrain, so radar only works on line of sight, so they have limited ability to see these tornadoes coming. And storm chasers refuse to go there because the hilly terrain, there's lots of dead ends, and they really don't want to get stuck with a tornado bearing down on them. That's the big push, is to reduce the number of deaths in Dixie Alley would be probably the top priority for this research. And you can, this kind of illustrates the problem. First, if you look at radar's been great, and it has had a big impact on improving warnings. Looking back to the mid 80s, that steady rise in the lead time and the POD, which is probability of detection, increased rapidly because of radar. But with how small these tornadoes are and the curvature of the earth, there's actually pretty limited range that you can actually see the tornado. Warnings primarily come from our knowledge of what the larger up above storm system looks like when a tornado forms. And if you look at about 2000, kind of our improvements plateaued. It looks like it dropped these last 5 years, but the truth is we're detecting more tornadoes. And that's why it looks worse. Reality is the older data really should have been worse. And the big one that those in tornado prone areas like where Oklahoma, is this false alarm. The red triangles here, they are the bigger problem. When I'm from Michigan, I moved to Oklahoma with a short pit stop in Pennsylvania before getting to Oklahoma. And, it was shocking the first time a large tornado was not that far away from us. And I saw people mowing their lawn and going to pick up food. And you start to realize that, the majority of the time they issue warnings, nothing happens. So most people in tornado prone areas ignore all the warnings. So this really pushed for some new approach to the problem, since for nearly 20 years, nothing has really changed. Looking back before radar, they thought that infrasound was a good possibility. There's work by Alan Bedard in the late 60s into the 70s that kind of got put aside once radar took off. But there's evidence that sounds below human hearing, which is infrasound, gets emitted from tornadoes and carries information about the tornado. And this is the motivation. And if you look at the problem of Dixie Alley, infrasound is not a line of sight measurement. So there's a lot of benefits that we'll kind of cover here as we go into basics of infrasound. So since I'm assuming not everybody is intimately familiar with infrasound, just kind of like the bullet points that about it and why it's a good fit for this problem. In general, infrasound is sound below human hearing, which is nominally 20 hertz. Though I'll say that I was playing for my family at different tones, giving ourselves a hearing test, and my 3-year-old daughter could hear. It hurt her ears when it got down to like 10 hertz, but nobody else in our family could hear it. So even on the low end, you have more of a range the younger you get. My 5-year-old couldn't hear it, but my 3-year-old could. So then if you look at, this is kind of just a generic map of nominally where different sounds sit, and tornado infrasound kind of is in the 70 to 80 dB range, in the 1 to 10 hertz range. General rule of thumb from observations is the lower the frequency, the bigger the tornado. Just from a physical scaling point, that kind of makes sense. Lots of things produce infrasound, both man-made and natural. I'll mention a little bit about some work we're doing related to earthquakes later in the talk. The one thing I was familiar with infrasound before working on this was really for nuclear blast, which is most of what infrasound research began as, was monitoring to see if anybody's testing nuclear weapons above ground. Because the blast these low frequencies can travel over long distances. So there's networks to monitor that. And that's one of the benefits and the reasons why this is viewed as a good possibility to improve tornado warnings. There's kind of two pieces that make it quite appealing. First is the stratosphere creates like an acoustic ceiling. The temperature distribution and wind profiles end up taking these acoustic waves and bending them back towards Earth. There was a volcano eruption where it was loud enough that they actually heard it go multiple times around the Earth. So if you get a low enough frequency that's loud enough, you can detect it over scales comparable to the Earth. And then atmospheric absorption, the lower the frequency, the farther the distance, which I would assume with this group is familiar with this idea. But the basics is the higher the frequency, you have more compression and expansion cycles per second. And as a result, each of those cycles, you're losing some of that energy. And so the lower the frequency, the less cycles over a given distance, you can go farther, obviously, with lower frequency. This is why you're either annoyed with your neighbor or you're the annoying neighbor with their bass turned up. I know I have a subwoofer here where I can listen to some of these sounds sped up a little bit into the acoustic range, and sometimes my colleagues tell me I need to turn it down a bit when I'm listening to them. So that is kind of the benefits and the reason why this has a lot of potential. But if you look at it, there's a lot of sources. They travel over long distances. It makes identifying the source a big problem. And so, we have our basic criteria for identification concomitancy, saying that the source is there, the signal should show up, but where it goes away, it should disappear. Is the direction that the sound's coming from tracks with, say, the tornado of interest? Characteristic signatures, is what we're seeing in the spectra consistent with what we know about from other measurements? This is one that is hard to do now because there's just not that many measurements of it. A big piece of our current work is trying to identify what is the exact signature of infrasound from a tornado. And then coherence. If we have multiple microphones over a relatively short distance, compared to these wavelengths, we would expect there to be high coherence between the microphones. Now, kind of a fundamental question, and I'm not going to get into the math that much, but should we even expect that if a tornado makes this sound, that we would get a unique signature? I kind of make the arguments from hydrodynamic pressure fluctuations of a vortice near a wall, and you can kind of make an idealized mechanism or vortice for that. And obviously those aren't acoustic pressure fluctuations, but the hydrodynamic pressure fluctuations are known sources of acoustic production. And what you can do is you set up those governing equations, and you can show that, for instance, you can't make the same signature with a weak vortice close to the ground and a stronger vortice farther away from it. So there's some fluid dynamics expectation that the fluctuating field should be unique to the structure of the vortice near that wall. And hence, similarly, we expect a unique acoustic signature, which we are searching for. So now to diverge before we get into the content is, anybody that knows my background would say, well, what are you doing working on this problem? My background is experimental fluid mechanics. Where are you doing atmospheric acoustics? And this is the part where I think it's helpful for students to see some of the path that how you end up where you're at, and how the pieces can kind of come together even when it's not obvious. From the intro, it said that I did my bachelor's at Western Michigan, graduate school at Michigan. I worked at Applied Research Lab at Penn State for 3 years before joining Oklahoma State. Before going to Oklahoma State, if you looked at my background, you'd say, okay, Brian Elbing does experimental fluid dynamics primarily on Navy-related problems, particularly with drag reduction. But what isn't necessarily obvious is during my master's, I did an internship at NASA Langley Research Center for Alan Zuckerrohr, pictured here, and we studied high-frequency acoustics, so sounds above human hearing. And we were trying to develop a calibration technique for non-traditional microphones, so like MEMS and those kind of microphones that were coming online, and we wanted to be able to calibrate them. We got up to 80,000 hertz for a calibration method. I go and do that acoustics experience I really enjoyed, and I went and I told Dave Dowling I want to do acoustics at the University of Michigan. I set up a meeting with him. He said, great, you're going to do fluid dynamics. And they put me on a project, and I learned a lot about fluid mechanics from these three men. And it was a great experience and is really the core of my background. Fast forward, I joined Oklahoma State, and I get a call 9 years later from that internship from Alan Zuckerrohr. And he said, Brian, I see that you moved to Oklahoma. I have always wanted to measure the low frequency sounds from tornadoes. He passed away shortly after that conversation, actually. But he piqued my interest enough, and I started reading up on it, and I realized that I was in a good position to tackle this problem. Not just because I'm in Oklahoma where tornadoes are, but it was at that point, I would say the acoustic side, there was strong evidence that yes, there are sounds produced from tornadoes. The key question to be able to use that is answering what is the fluid mechanism responsible for the production, because that is how you'll connect the sounds we're hearing with the flow structure, which is what we need to know if we're going to interpret the sounds we're receiving from a remote location. And so I, as an assistant professor, I said, let's take a gamble here. It's not the only research I do, but I started putting resources towards this. A key piece was NSF funding a project actually developing drones to monitor and improve forecasting of weather, which is, again, not obvious what infrasound piece would be in there, but I had a task inside that proposal, that large multi-university proposal, to say, well, what if we could understand this infrasound and use that to direct resources, which would be the drones, to critical locations. And so the target here is reducing false alarms by using infrasound to target atmospheric measurements to give key information to reduce false alarms or increase confidence level. Since then, we've gotten other grants and we've grew our team. These are 4 professors that are primary contributors to this project. Got a nice team of graduate students between the University of Nebraska and Oklahoma State University that are all contributing to this, both on the observation and developing tools to be able to use this data in real time. The key piece that came out of that first grant was that we were able to deploy our first infrasound array at Oklahoma State University. Conveniently, Oklahoma State University is an ideal location for monitoring tornadoes from ground level with for their infrasound. Those that have been to Oklahoma or spent at least a tornado season in Oklahoma are familiar with the storms run northeast. They go from essentially Norman, Oklahoma area towards Stillwater, Oklahoma. And you want to be, for ground-based measurements, you're ideally downstream. That's my Navy side coming out of how I think about the problem. Downstream of the storms. And so Stillwater sits right in line with the path that's commonly taken for these large tornadoes. So it's a great spot to be. And that's why we deployed it there. And we've been monitoring since 2016. The system's actually down right now because for maintenance, but more or less since September of 2016, we've been monitoring the atmosphere. In 2020, we got a second array, and it was deployed this last year, and we'll get into a little bit of the 2020 season. But for the most part, COVID handcuffed us, and then the season, because the polar vortex didn't produce many tornadoes, so there wasn't too much from 2020 to discuss. All right, so that's how I got involved and where we're at with resources and tools. Now I'm going to go into some key observations. So if you look at, so we started recording in September of 2016. This is the way this research goes. We deployed September 2016. Like 2 months, in the 2 months before that, there were 2 tornadoes very close to us, 2 large tornadoes. Then we had exactly 1 tornado after that until 2019, when that historic year hit. And I'm not going to go through each of these tornadoes. Instead, I'm going to hit this first one, this 2017 one, which is the most well-documented one that we've observed. And then I'm going to go into the 2019, 2018 seasons and just show you some observations and what that kind of tells us about what we expect and how it sits relative to what we already knew about these. All right, so in May 11th, 2017, near Perkins, Oklahoma, there was a tornado that formed out of a large convective hail-producing supercell. The tornado was small. It was originally listed as EF0, but they changed it to EFU, which just means that they were unable to determine the tornado strength. But the path width was 50 yards. The length was 0.1 miles. It's a small tornado. There's like one video of it here in the bottom corner. You can barely kind of make it out, that little hook there. It's a relatively small tornado. We were in the top right from this radar image. You can see where the tornado was, and we were about 12 miles away from it with our infrasound array. And with infrasound, it's really important, not just your distance from it, but your orientation relative to it. We were kind of on the edge. If that tornado formed any farther northeast, we probably wouldn't have heard it. The wind profiles definitely during these storms, in the one direction, it'll bend the arrays away from the earth, and you'll need elevated measurements to get it, or you might hear it 300 kilometers away, even though you're not going to hear it when it's 10 kilometers away. So the orientation is really critical, and we were just barely in the range of where we would want to be. Furthermore, this is kind of a perfect scenario for us, because on the left here, that big black ring is locating where you want to be within that ring in order for characterization with radar. Anything farther, you're not going to get meaningful information about that storm system. And this is really pushing the limits. And you see that tornado shown by the red dot is just barely inside of that ring, while still being just barely in the orientation where we would expect to hear it in Stillwater. On the bottom right here, we have like kind of the time history of different metrics that we pull out of the radar data. One that's important to note here is there's this big peak it's called NHAE, which is basically measuring how much hail is being produced in that storm system. And with the large peak formed before there was infrasound production, which we'll get to that, where historically there was a lot of thought that maybe it was the hail production making the infrasound, not the tornado rotation. Similarly, there's questions about what is it, the larger storm system that makes it, but the peak in the larger storm system rotation, which is these red circles, peaks again before the peak in infrasound production that we we see. I haven't shown you the infrasound, so I probably should have that on that chart as well. But here's the time trace of the infrasound now, or at least two of the microphones. And we get these two big bursts, and they line up with when the tornado touched down. This was what caught my eye. That said, okay, this is very promising. But as you dive into it, actually most of what you're seeing in the time trace, in the bottom here, I'm plotting wind speed versus time. And you see that those peaks line up with when the speed exceeds 5 meters per second, which is the dashed line there on the wind speeds. And that's kind of an indicator that wind screens for infrasound aren't that great above 5 meters per second. So I looked at the spectra, and most of this did look like just wind noise. And I took from 0.1 hertz to 5 hertz, and I plotted it versus the wind speed, and you see this nice correlation, increasing noise levels with increasing speed. However, in the 5 to 50 hertz, I'm going to show you the spectra in a second, where the structure looked different. I did the same thing, and I plotted it, and you see, oh, I do not see a correlation. The only elevated points at all correspond to when the tornado was on the ground. So that gave some confidence that, okay, most of that signal we're seeing in the time trace is noise, wind noise. But there does seem to be some other signal where we also see high coherence between the microphones that is not wind speed. So we jump to the spectra now. On the left here, comparing during the tornado, before and after the tornado. The highest peak here below the that's I see here that the axis is wrong on this left plot. The right one is definitely correct. So that should be 10 to the 0 and then 10 to the 1. No, 10 to the 2. Yeah. That's weird. Sorry, there's something wrong with that plot, and I don't know what it is off the top of it. But that cutoff, that dashed line, that's supposed to be 5 hertz. I don't know why the x-axis doesn't make any sense for that. But the structure itself is correct. I've looked at this enough that I can assure you that. And we saw like a 10 dB rise from the background levels before and after the tornado. I'm not going to get into the event 1 and 2. There was some thought there was a second tornado that touched down later from the same storm system, but it was never confirmed because the storm was rain wrapped and they couldn't get a good visual. Here's a replay. I don't know if this will come through. I have a subwoofer, but the speaker doesn't necessarily play it. Maybe you can hear a little rumbling. This is just playing the 5 to 50 hertz back, sped up into the audible range. I think it's like 4 or 8 times faster. So this peak that should be at about 9 hertz then becomes, if it's 4 times faster, it's going to be in the 36. So you get that rumbling sound is what we get. So then what I did is I took just that 5 to 50 hertz band, and then we looked at the bearing angle of that signal and compare that. So the blue diamonds here are the direction from the sound. And then the green solid line is the path that the core of the storm took that produced the tornado. And so at relative time equal to 0 is when the tornado touched down and it intersects that red dashed line. That's the bearing angle where the tornado formed relative to where we were measuring. And you can see that both the infrasound kind of tracks with that storm system for the most part. And at the time when it touched down, the signal seems to be pointing in that direction. So we have some confidence that part of the signal is in fact associated with a tornado. I'll come back in a little bit after we kind of go through a bunch of observations on, okay, now if we're assuming this is the tornado, what does it tell us about the fluid mechanism? But this is the tornado. If you've ever seen any news or press about my work, it's almost certainly this tornado that they're talking about. It's been covered by a lot of news outlets. But just a reminder for all the students out there that what's most important is the journal article that came out of it. It was peer reviewed, the data, we have confidence in it, or at least the assumptions that we needed to make were explicitly made to, and that's the real value. So the paper in the Journal of the Acoustic Society of America. So now I'm just going to lightly hit on a bunch of different observations and kind of things that we're looking at, and both the unexpected and curious, as well as the informative. So, like I said, 2019, we had just a lot of tornadoes. And for the most part, the spoiler of this part of the story is that it was mostly disappointing. And it really pointed to how we had to change our approach. And I think that'll come through a bit as we go through these observations. So here's an EF1 tornado that hit relatively close, like once again, about 12 miles from our array, but now it was to the north of us instead of the south of us. And it put it really where no radar could get us. So radar is out of the question. We look at the infrasound bursts, and the bursts kind of align in between a significant hail event and a significant tornado, and the tornado that we're discussing, which kind of leaves us confused, where there wasn't that much information or storm system development. We're looking into propagations. There's a good chance that that's playing a role here. We're actually putting a lot of resources into modeling propagation given storm system and variable atmospheric conditions, which isn't done that much currently. May 14th, 2019, we had, I was actually, this is kind of an interesting story where I was at home and I was putting my son to bed. And whenever there's storms forming, I have like a cheap infrasound microphone where we can plug in my computer, so we can kind of watch a signal coming in as it's happening. And I hear the hail start to hit the house. And so me and my son, we run downstairs, we plug in the microphone, and we're looking at the signals, and there's nothing. It's flat. It's like nothing's happening, which is not typical. Usually when there's a strong system, hail producing, some signal shows up. And I was really surprised. I thought, well, maybe there's something wrong with the microphone. So I checked my array and really no signal. And so then we went to radar, and what we saw in the storm system was quite unusual. This part of the storm, there was almost no rotation. On the right here, the radar, if there's rotation, you would see kind of a contrast between red and green. And looking back on the history, when they thought hail was a significant producer of infrasound, Alan Bedard at NOAA did a study, and he found some large storm systems that had relatively straight line winds, so not rotation, and produced significant hail. And they found as long as there was no rotation, hail produced no infrasound, which there's some ideas about how it might, given the general process of air being lifted during the hail production. But yeah, this gives strong credence to that position, that if there's no significant or tight rotation, there's no sound produced. Contrast that with a few months earlier, I had gone into work, and my colleagues were like, "Did you pick anything up on your microphones from yesterday?" And I was aware of some tornadoes, but they were pretty far away. I said, "Oh, I haven't really looked at it yet. Those tornadoes are so far away, it's unlikely that we would have heard anything." And they're like, no. There was a funnel cloud that formed almost over your microphone. So the plot here, the star is where the microphone was. Just to the north is the airport, and just on the tip of the airport, there's this tight rotation that passed by. And I check, and sure enough, we have this coherent signal with a burst that lines up with the formation of that funnel cloud. So now it's a much weaker storm system, but you're getting that rotation. It didn't make a tornado, just a funnel cloud. And we got this burst in the frequency range we would expect. Another tornado, this EF0 tornado that was again close to our array. It's a bit noisy, not that strong, but there is some structure that kind of looks similar to what we see out of a tornado, and this is kind of surprising. This is what's called a QLCS tornado. There's some thought that this would not make infrasound, and I wouldn't say this is definitive at all. But it's interesting that we got something that looks similar-ish in the frequency range we would expect. But again, we need more observations really to gain any confidence. And this is a testament to always being diligent. I had checked the night before on my system, knowing that in the morning there would be some storm systems developing. I got up in the morning, checked again, and the system had crashed over the night. I got it up and running only minutes, I think, before the tornado actually formed. So I definitely prefer having a longer window before and after a storm goes through. But at least we're able to get it up and running and recording during the tornado formation. Then the final observation that I'm just going to hit on here is this outbreak on May 20th of 2019. Professor Howard was in Oklahoma at this point. He would definitely remember this day. This map on the upper left, all the red dots are tornadoes that formed. All the purple is where large hail was produced on this one day. And we're almost right in line with the storm that was passing through and producing all these tornadoes. So this was a very promising day. We should have something. When you start plotting what we have for radar data, so in this plot on the right, the blue and the black lines with the open circles, that's metrics that are coming out of our radar data. And what you see is that it cuts out almost exactly before we get our first tornado. We then get an EF1, another EF1, another EF1, two EF0s, an EFU, and we have no radar data. It's sitting in between where they're going to be present. The green is the infrasound spectra from the 5 to 40 hertz. We get some peaks in there, but the bottom line is generally where the signals were close to us, the radar was out of range. We're doing the modeling of it in the bottom left there, showing that we've modeled some of these tornadoes to start looking at as dependence. And you can see the difference between these is all we did is we lofted the source from 0, so it's at the ground, to 1 kilometer above ground, and you get these different patterns. And if I won't get into the specifics of how to read this, but essentially it kind of tells us an idea of whether or not at the ground we should expect to hear the signal. And you can just quickly see that's very sensitive to the elevation. And then this was just putting in a single atmospheric profile. But we know there's major differences between these storm systems passing through. So this is where we're putting a lot of effort into being able to model, given our best guess as to what the atmospheric conditions were during that event. But the big story from here is we realize we need to increase our odds by making our infrasound measurements mobile, which isn't a trivial task, but it's where we put our focus in after this 2019 season, where we had all these opportunities and really we're always getting one piece of the information and not two pieces or more. So that kind of gives you some sampling of observations that we've had and what they're telling us, and really what we need. For recent activities, I'm going to get into what have we learned from those observations and what are we doing to solve that problem of we need to be in a position to measure the tornadoes and get radar data at the same time. So first on the mechanism, so I would say there's 3 strong candidates for what is producing the sound from a tornado. The first one is radial oscillations. So if you picture the tornado as a column of rotating air, and then you picture the radius of it expanding and contracting, right? So now you have kind of like a cylinder speaker. This was originally proposed by Abdullah in 1966. So this is very early on the research. And subsequently, the work of Schechter has really shown that it's non-physical solution. Okay, so this is the big knock on this mechanism. But even in Schechter, he acknowledges that, well, maybe you're running into these problems just because Abdullah's work had such a simplistic fluid structure that you need to incorporate some of the complexities and the dynamics of the tornado itself in order to solve those non-physical limitations. And I think there's strong evidence in this because if you look at the May 2017 tornado, well, we saw in the left here, I plotted the overtones. So we had the fundamental peak and then we had some higher peaks. And I plotted those and they're linear. But they're non-harmonic. So there's not an even integer between each harmonic or overtone. And Abdullah's work predicts linear non-harmonic overtones. Comparing with his work, we don't line up, but you can see that the general relationship seems to be consistent. Similarly, on the right, I took all available observations in the literature, which isn't that many, and I plotted it versus what they predict between the fundamental frequency and the size of the tornado from Abdullah's work, and it kind of follows that trend. But you would expect all these points to actually fall on the solid line, which they don't. But the functional form seems to be consistent. So I would say there's some strong agreement with the radial oscillation viewpoint, but there's some more physics that has to be teased out to solve the problems that Schechter has identified. Number two, this is actually what Alan Zuckerrohr thought and his colleagues, that non-equilibrium pressure relaxation effects impact it. The reason why is because the red dash part of the governing equation, so this is the Navier-Stokes equation reformulated with non-equilibrium effects incorporated. When you do the analysis, you would drop off that part of the equation, the one that has a red dash line around it, because it should be small. And then what's left, it actually is the only analytical result that accurately predicts the pressure inside of a tornado. So we only have 8 measurements of the pressure inside of a tornado. This is the only formulation that predicts those values. And what's interesting here is that the part that gets thrown away has been shown to be a wave equation. So we have a potential mechanism to propagate sound that's related to the structure, the flow field of the tornado. And then the third is this is more of the view out of the Colorado group, that latent heat effects coupled with a shear instability are responsible for the production. And there's strong evidence to support this view, but their connection between the shear instability and the latent heat, I don't see yet. And but I would say the latent heat, there's strong evidence that is required to make the infrasound. And the shear instability would connect with the flow field, but the connection between those two pieces is not obvious, at least to me. They haven't published much on it, so I can't. So it's also hard to know if I'm just not aware of a piece of it. So that's kind of where we sit with the mechanism. The bottom line is to separate those pieces. We need more observations of infrasound with flow measurements. So what are we doing to solve that? One thing we're doing is we are deploying mobile sensors with storm chasers. So this is Val Castor and his wife Amy. They're storm chasers for Channel 9. They've agreed to carry one of our microphones that we installed inside their vehicle along with some other instrumentation. Yeah, so they chased through the 2020 tornado season. Like I said, 2020 was pretty tame in terms of tornadoes in Oklahoma, at least. But we got some major hail events. We got a tornado event with an elevated signal of about think it was about 10 dB above the background when a tornado formed, and it's kind of in the same frequency range we would expect for a small tornado. This was in Kansas. And we have some funnel cloud. There's video there of the funnel cloud. And we're going through these observations. They're obviously pretty noisy and take some work to tease out the information, but what's nice is it removes the questions about propagation effects. We're also doing airborne measurements. We have some work equipping drones with sensors for really kind of a separate project. And then also for another separate project is we're using these solar balloons. And the idea here is that you use the heat from the sun to heat the balloon. It lofts to about 20,000 meters. And then it stays at that elevation all day long until sunset and then comes down. This work is actually for the studying of earthquakes. So we were recently funded on a joint collaboration with NASA JPL, Caltech, Sandia Labs, ourselves and OU. We're going to fly these balloons over Oklahoma with infrasound sensors to study earthquakes as a demonstration of how this could be done in Venus. Venus, the surface is too hot for any instrumentation that exists today. So the idea is, can we get some instrumentation floating within the Venus atmosphere at where the temperatures are acceptable? And so we're using Oklahoma earthquakes as a demo for how we could get Venus quakes to identify the structure of Venus in the future. We'll be starting these tests. We're actually starting now. We're already launching, but the majority will be over the next 2 summers. And the benefit here is there's still going to be storms during those summers. So we should have balloons lofted during storms these next 2 summers. So in conclusion, infrasound has been observed to be associated with tornadoes and tornado formation processes, but more observations are needed. Number 2, we have several observations. Some still need more analysis, but there are some interesting preliminary results. Number 3, what we really need is 1, increased observations, 2, co-locate microphones with radar, and 3, identify fluid mechanisms. Which now I realize I should have also put that new infrasound array, that's mobile, and we've secured locations near radar. So the idea is we have the storm chasers, and we're looking at the forecast, and we're going out ahead of the storm and setting up our array next to radars in locations where we expect the storms to pass through. And with that, I'd be happy to take some questions. Hopefully I didn't roll through that too fast, or that it made some sense.
No, thank you, Brian. That was very interesting. If you have, for those of you in the audience now, if you have questions, feel free to either weigh in and ask them, or you can put them in the chat box as well, and we'll watch for those.
I had a question to start, if that's okay.
Go for it, Jen.
So I go to sea a lot, and we see water spouts that happen out there. Has anyone done any acoustic detection or characterization of water spouts that you know of?
I hear people talk about them a lot. I've never seen data for one. And I don't know, like, there's been hurricanes, that's a solved problem for the infrasound production. But no, I haven't come across much on water spouts. Same with like dust devils. People kind of report on them. They say, yeah, they're around, but I don't think they make strong signals, is what I gather, because I just haven't.
I imagine they'd be hard to measure too, because you just never know where or when they're going to form.
Yeah. So, I mean, the dust devils, actually, they've had success with, like in Australia, where they have the nuclear monitoring sites, and there's some of those locations close to it where dust devils form all the time. And they pretty much have said, yeah, it doesn't produce much of anything of a signal. But I have been curious about water spouts. It seems like that might be a stronger possibility.
Thanks. Very cool work. Thank you.
Thanks.
Yeah, I have, see, maybe Jen, you can help me kind of monitor the chat, but so you mentioned something there at the end, Brian, about needing to co-locate the sensors, the acoustic sensors with the radar. And it seems like you've got the acoustic sensor prep down pretty small, so you can put it in a drone, you can put it on top of a near monster truck for chasing storms. What about radar units that are a little more portable, or instead of these big fixed units, which I'm assuming that's what you're using across the? Is there
Yeah.
any promise
So,
for downsized radar units that are a little more mobile?
yeah. So there's, we work, I've written some proposals with OU's Advanced Radar Research Center, and they have the mobile radars.
Yeah.
They're in high demand. So the key is getting the funding to support the dedicated use of one of those. OU's been supportive of this project in general. We just haven't landed the grant that would really
Yeah.
fund that piece.
One of the questions I was thinking about when you were talking about you had a couple different arrays you had set up. Oklahoma, a lot of people may not know this, but Oklahoma has a really interesting weather monitoring network there called the Mesonet system, and I don't know that there's anything like that really in any of the state. Have you ever used any data from Mesonet, or is there any promise for integrating that network into the work that you're doing?
That's a great point. Yeah, you're right. So there's other states that have tried to mimic Oklahoma's Mesonet. Kentucky has one. I think New York's tried, but really nothing quite comparable. And for those that aren't familiar, so basically every county, I think it's has at least one Mesonet site in Oklahoma, and I think total there's like 120-ish sites that have a tower, and it's instrumented with at least a subset of wind, temperature, moisture, those kind of sensors. Um, I do use that data, so that's primarily how we give ground level atmospheric states. Is we pull the Mesonet data. We've been in discussion with them about deploying at their sites. In fact, I think we went around, we got approval for our infrasound array, basically getting permission from certain properties that, yes, you see a storm, you can go into our property and set up your system. And I think every single one of them has a Mesonet site. They're not all owned by, well, they're all kind of privately owned or by some group, but we've got all the ones that we have permission also have a Mesonet site.
Cool. Yeah, it seems like a great resource that would presumably kind of support some of your aims there. There's a question in chat, and I'll just kind of read it off from Aditi. She says, "Thank you. Very interesting. I'm studying the impact of hurricanes on ambient sound underwater. I saw in one of your plots that you had defined a before and during period for impact from the tornado. How did you define the before, during, and after time periods for your analysis?"
That's a fantastic question, and one that is not well answered. I actually use when I'm trying to illustrate the problem of studying this, I use that 2017 tornado that gets all the attention, and I say, that was a tornado. There's a lot of good and bad that when you look at that. On one hand, I can say, well, there was no warning on that tornado, so I was, it was close enough to my house that I was home and I was paying attention to it, and we saw a video of it on the ground before there was ever a warning. But I had that signature 4 minutes before touchdown. Okay, so that really points to the infrasound production being associated with formation processes, which is consistent with other people have seen. But how do I interpret that result? What if the storm shifted and the tornado didn't quite touch down? It barely touched down. It was only on the ground for 1/10 of a mile. Now suddenly I would say I had no tornado, and what's the signal I'm getting? And so that question is a great question, and one that's not easily answered without, I would say, really you need storm chasers with radar, because I need to be able to see that structure at the ground level, and the connection with the infrasound production to answer it. But in the paper, I'm very honest about, I can point to all these things that that's kind of consistent with it being production from that tornado, but in the end, it's a best guess. I even argued that for why it should be published is not because this is definitive, but because you can't wait for definitive answers before you start looking at collective. And
Yeah.
so I was very honest about there's questions that still remain, but this seems to be consistent with what we expect.
Very cool. Thank you. So I had one other question, maybe one and a half. Any others have those, throw them out now. And we've got just a couple minutes left here. But so you talked a lot about infrasound, but your early work was actually with ultrasound. Do tornadoes produce any ultrasound at all? Is there any signature above human hearing threshold that they produce that you've monitored?
There is some evidence. Roger Waxler is another big researcher on this, and he's put out a paper with his colleagues, really showing that there is some evidence that there's some coherence at audible range from tornadoes. And he's kind of shown that it follows kind of a aeroacoustic, like jet turbulence type signature. Higher than that, it'd be really hard to answer that. Most of the noise, I get that question a lot because they say, well, those that have been really close to a tornado describe the sounds of like a train bearing down on them or something like that. Most of those sounds have been shown to be associated with turbulence going around different buildings and structures. Yeah.
Yeah. And I would think it would probably attenuate, much more quickly than infrasound would as well.
That's the other thing is it's going to be incredibly noisy, right?
Yeah.
There probably is something in there, but it's going to be buried in the weeds of.
The other question would be how close would you have to be to it to detect it, and do you really want to be that close to a tornado? So I'm an animal biologist and study animal communication. So I always think about how animals respond to these sorts of events, and there's been quite a bit of evidence that different animals can detect substrate-borne seismic vibration produced by earthquakes and such. Anything? Do you know anything about any animals that could be in effect biosensors or have shown a response to what would potentially be the infrasound signature in a tornado that would be something to investigate?
Yeah, there's a few examples. Probably the best one is elephants in Africa. They'll watch a herd of elephants and they'll be moving in one direction, and then a large storm system very far away forms, and they'll turn and start heading towards it. And it's far enough distance that there'd be no sensible change in pressure or wind speed or really any other sense other than infrasound is about the only signal from that distance that you would expect them to be able to receive. And so it's generally believed that they're hearing infrasound from a severe storm that's developing, and then they're heading towards that storm to look for water.
And it would be a large enough sensor to couple something in that frequency range. Yeah. The question becomes, is it more likely to convince a funding agency to pay for small mobile radars or for installing elephants across the landscape in Oklahoma, I suppose?
Yeah, right. What I often get, my dog does this, where if there's a storm within 100 miles, she freaks out. And I think most people relate to that. And so they're usually like, well, should we just put accelerometers on dogs to sense?
That's right. Well, Brian, I certainly appreciate all the exciting science that you shared today in your talk, and appreciate your willingness to come and share your science with us. It would be great to have you back again sometime when you learn more. And of course, at some point in the future, when I'm back out on the prairie chasing prairie mole crickets in the heart of tornado season, we'll have to definitely stay in touch.
Yeah, absolutely. We could have you give a talk on Inside Acoustics in Oklahoma.
All right. Well, appreciate everybody being in attendance today. And again, we'll see you all in December. And we have another talk coming, one last final talk in our series for this semester. And as always, appreciate all of you joining us for these exciting tidbits that have acoustics threads within the fabric of these exciting studies. So Brian, have a great time in your remaining of your semester. We'll see you. I'm sure our paths will cross again soon.
Absolutely. Thanks again.
Thank you, Brian.
Jennifer.
Good to see you.